All right, let's begin here. So we just talked about a little bit about this last problem that we did here. So we had to start and do the quadratic formula because that was only available for us for factoring purposes. And then what we had to do is we had to figure out the angle measurement that makes that true. So for this one, initially, this one is not possible because this number, as you put it, it's gonna be less than -1. It's -1.3 something or something. That don't work. Anytime you get a number that's greater than +1, that's also not gonna work. That's fine. But we want to take just extra little time to take a look at this here. So the number that does work has to be a number that is between -1 and a +1. We good? Okay, that's first things first. Then let's talk about a calculator. In order to punch into the calculator, I always tell you guys, please change it into a positive. Whatever it is, make sure it's positive before you take the value off of it here. So because it brings you into the quadrant 1, because it gives you the reference angle. So for this particular one, we actually want the reference angle. So we have cosine. Let's see, I'm going to do it step by step. -1 plus square root of 3. I'm going to do it in parts here, just real quick here. Is that? Is it okay there? I'm going to divide this by 2. Is that okay still there? And it turns out to be positive. That's cool. So cosine inverse, but hold on, make sure I am in degree mode because this thing always goes into radian mode. So cosine inverse, of that stuff. Now, if you are going to write out 0.36602, write out at least 5 decimal places accuracy because at least gets you the value. Or you could just do this here. You got yourself your second and your answer. Are we good there? Done. 68.5. Good there. Okay, let's see. Just out of curiosity, what happens if it was a negative? So now let's play with that here. So I'm going to do the same thing here. It's -1 plus the square root of 3. There's a lot of mental math here. Divide by 2. We're good there? So I'm going to say this. I'm going to find the cosine inverse of negative of my answer. My question.
No,
That's totally off, huh?
hey, that's 1
No?
minus. Yeah, hang on. Are they the exact same thing as that? Well, one. You did.
That is definitely not a reference angle, huh? That's above that. Yeah.
But that's not -1 minus.
Oh, yeah, negative. I have. Sorry, guys. Say again. Say again.
I don't know what's going on.
Okay, so real quick, I just did this one right here. -1 plus the square root of 3 divided by 2. I just did this one right here. But I stuck a negative just to sort of see what happens if you keep your negative in the cosine. Did Isabel do something wrong?
No, I was just confused as to what you were putting.
Okay, gotcha. So it was -1 plus root 3. And then negating that, just so you guys, real quick here. Look up at the screen, see what happens here. I'm gonna go 180 minus answer. What are we good? So that value there that had a negative cosine, right? It sticks it in quadrant 2, but the reference angle will still be the same. But you're still trying to figure out the x coordinate away from the origin, right? If you go left or if you go right, you're still away the same amount away from the origin.
If it's a negative, it's just 2 ways minus.
So for sine, again, we're just playing around, okay? Real quick here for sine. Let's say it was sine inverse of a point, I don't know, 78, right? That gets you 51 degrees. If it was a negative, no problem with sine, right? Like, okay, fine, just turn it into a positive. I'm back into quadrant 1. We're good. Same thing with tangent, because tangent is an odd function.
Is it always
Good, good.
being quantum?
Again,
Is it always being quantum?
our reference angle begins in quadrant 1, and then we move it wherever we need to go.
I was gonna say, isn't negative 51, that's still a reference?
Yeah, so with negative 51, that's the reference angle. We think about it as a reference angle, and then we have to add 1. We have to figure out how we're going to do that, right? So let's do that here. Let's see. Because our answers finally have to be between 0 and 360. That's our issue.
So you just add 360 to negative 51.
Uh-huh. Sine inverse negative 0.78. And so you guys can do a lot of this by calculator. So if I see this right here, I'm going to add 360 to it. Is that right? Because I know I'm 51 degrees away from 360. So plus 360, 308. Okay, does that help? Does that make sense?
Yeah.
I use the calculator. So now let's get something. So you're not ever going to get something in quadrant 3 because of this little idea here. So let's do a little bit more things here just to make sure we got it here. Okay, so the reason why you're never ever going to get anything in quadrant 3 is because sine inverse works in quadrant 1 and 2. Everything's positive here. Okay, let me do that again. Give in just a second here. Yep. So sine inverse, I'm going to just say of x, because it has to have a variable after it each time here. Sine of x and sine inverse of x. They work in quadrants 1 and 4. Cosine inverse works in quadrants 1 and 2. That's why. We're good. If it's positive, it works here. Any negative values are going to work here. Any negative values here. Technically, any negative values for even functions are going to work here. Any negative values for odd functions work here for the most part. And then there's one. Of course, there's always one. You know, always one of them in the crowd. So sine and tangent are odd functions. Yeah, and we don't worry about these as much because our calculators only have sine, cosine, and tangent, right? So we're never going to sort of have to think through that. Okay, so then secant works here because it's an even function. It also works here. Cotangent, of course, all of them work in quadrant 1, right? Because it's the positive case. And then the fun one. You guys ready for this? Cotangent works here.
And this is exclusively for.
This is exclusively when you are taking the inverse by calculator.
What do you have to quadratic? Okay, is this on the like note sheet that we get? The formulation? Yeah. I don't think it is. Yeah,
I don't think so. So we should.
Do we have to memorize this?
That should be something we should have a copy of. I don't mind making a copy of it. You guys see it here. It comes from this right here, guys. Real quick, just so we know. The reason why this works, let's do sine first, and then we'll do cosine. So it's sine. The reason why this guy works, right? It's fun, just kind of putting a few things together since we've been studying it. Okay, think with me for a little bit here. Sine function. It passes the, again, just kind of reviewing a little bit here, but I think it's useful. Chop it up so it passes a horizontal line test. Horizontal line test says that when we take the inverse of this function, The inverse will be a function.
Or anything that
So-
has.
A horizontal line test specifically says. that
Yeah, it says if a graph passes the horizontal line test, then the inverse of the function is a function. But and I can write it out if you need for me, Dylan. That's no problem. I mean. Okay, so we chop right here, is that right? Chop right here, like this. Cool, yeah, and notice what happens here. It is from -π/2, which is quadrant 4, and to π/2, which is quadrant 1. Okay, very good there. Awesome. Tangent, the tangent curve. Love it. You guys remember the tangent curve? Anybody remember how the tangent curve looks like? Okay, yeah, it goes like this, like that, and they have dashes right here. So -π/2, then π/2.
Same thing. Just cut it negative.
Yeah, so the most natural way of cutting it is like right here. Cut all this off, cut all this off. There you go. Quadrant 4 works. Quadrant 1 works. So it's almost like this little connection, like that. That's so cool. So if it's even function, if it's odd function, it just cuts naturally like this. Because an odd function has, right, positive x, positive y gives you negative x, negative y. So it is symmetric about the origin, right? Or quadrant 1 is a mirror reflection of quadrant 3. Okay, quadrant 1 and quadrant 3 are mirror reflections, and because of that, you can have the horizontal line test here.
So then you're kind of actually, you have quadrant 4, but next to it, you want.
No problem, guys. And again, you guys are super cool because I like these questions. Because remember when we take angle measurements, this is going positive, but if we go this way, this is just going negative. If you go negative 90 degrees, this would be -π/2. It is quadrant 4 in the way we think about it. Now the question is, which degrees do we want there? So this guy can range from 0 to -π/2. This guy could range from +3π/2, which is down here as well, to 2π. Those are nice, perfect ranges for quadrant 4. Back in just a second here. We're good there? And we can loop all the way around 2π, 2, 6, so 3π/2, 4π/2. Quadrant 4 also can be 2. That's still a measurement of quadrant 4. True, true? Yeah, so it don't matter. Okay, hold on, sorry. 4? No, sorry. 4, 5, 6, 7, 7π. There you go. 7π/2 to 4π, still a measure of quadrant 4. Is it that good? Max. Sure, absolutely. We didn't cover it explicitly, but when we and this is a presentation you can do if you like. Sound wave by cosine or sine, absolutely. It measures electricity, AC currents. It measures sound waves. Perfect. So if you guys want to do a presentation on the sine wave and the sound wave, absolutely. There's a person that was talking about, I don't know if I mentioned to you guys here, the difference between a digital sound and a real sound, right? And it was the sound wave. But what happens in a digital sound, because it's coming out as one single tone, this is interesting. You get one sound wave. That's all you get. You just get this pitch, and that's it, right? On a, let's say a person's playing a piano, not a piano, sorry, too many instruments, too many. Oboe, saxophone, violin, if you do that, right? So if you go with the violin, what happens is you get a much fuller sound. And the reason for it is because you actually have multiple sine waves happening in your ear at the same time. It's just a different frequency, so we hear this full sound. And so that makes an instrument so much more grand than other instruments. So the difference between a Steinway piano, right, versus just a regular sort of piano. Why? Because of the wood, because of the contour lines of it. When you hit that note, it makes a fuller sound. And again, it's all about how do you adjust this little sine curve to get you that perfect sound. Interesting. Saxophones, same way. So you can get a cheap saxophone and then have this almost like sound to it. You get a nice saxophone, it will have more of a, not the screechy sound, it will more of a full, just a full sound with the other undertones underneath it. So yeah, Max, go for it, man. Absolutely enjoy it. Okay, guys. So that was tangent. Let's do cotangent. So where's the natural break that you guys see on cotangent? Let me graph it for you. That's pi over 2. This is pi, and it goes down again.
You swap it out to 0 pi.
I'm saying it's different from sine and tangent. This is in.
And then this is the natural break, right?
Yeah, but it's still relatively easy because it's zero.
Okay, what do you guys say? Where's the natural break for cotangent? Yeah, 0 to pi, even though it's an odd function. Notice that these guys match here, right? As you go down here, it's going to match down here. So it matches, the quadrant 1 does match with quadrant, sorry, this is in a sense, yeah, quadrant 1 does match with quadrant 3. It's an odd function, but yet the natural break of this graph is from 0 to pi, or quadrants 1 and quadrants 2. Awesome. Okay, here it is. You guys ready for this? When I was in school, you know, when the dinosaurs ruled the earth, here it is. The natural break that mathematicians thought that cotangent should be was still quadrant 1 and quadrant 4, quadrant 1. I grew up doing this right here. So what happens in mathematics, it's the strangest thing here. So isn't that weird? We get a break. There's nothing at 0, right? It's undefined.
Yeah, because either one's going to be 0.
So then cotangent has a weird break right at 0. Otherwise, we're going to use quadrant 4 and quadrant 1. And what happens is as we build more and more mathematics out, and then what happens is we reflect back, they're like, you know what? That's not a good break for cosine. I know it messes up some things on the front end, right? But it sure is also the back end, but it sure is a lot better to work with it on over here, right? And so can you really think of something like that that happens, like when you learn something more, then you're like, you know what? Nah, it needs to be this way. We're going to learn it again. I don't know. Maybe I'm just thinking like movies. Okay, movies in general, right? Or a book, right? You read a book and then you reflect back like, oh, that's why he did that, right? Like, oh, that makes sense now that he was doing this. So that's a literature aspect of things, right? Painting cars, for example, right? When you have to paint, you have to mix paint with hardener. And that's the way you do it, right? So then when you reflect back like, no, it needed a lot more hardener in the paint for next time, right? So what do you do? Like you're correcting things that are, it will still work, right? It still painted the car, right? It's just, it started to chip 2 years down the road, right? So then you reflect, okay, that's the mixture that's better, right? So same thing here. Same thing happens in mathematics. As you learn more, you're like, whoa, I'm going to reflect back and I'm going to change this structure. Okay, let's jam. Okay, that was a good explanation. Was that a good explanation? Did I fill in a few holes there for you guys? Okay, so now let's go on to this one. Dun, 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 dun.
Oh,
Oh, hold on, did we even finish the last one? Oh, let's go back over here. Did we finish this completely? This is part A, right? So then for part, oh, sorry, this is part B,
oh,
right? Part A is just gonna be those exact same things, just with plus 360K. We're good. There's the end of it. No, that was a good, I'm kind of glad we took that time to explain that. That's important. Okay, this one is, it's called a horizontal translation. So now notice in the problem itself,
yeah. We know that at 60 degrees, right, that sine equals.
oh yeah, that's right. Hold on real quick, even to answer Abe's question real quick. Do we have sine all by itself on one side? We do, absolutely. We got some stuff inside the angle. That's weird, but we know sine. So the question is this, what happens is this? What is this right here? And Abe says, what degree measurements make that true?
60 or 30? 60, no. Yeah.
60, okay, yeah, the y value is bigger than the x value because the x value would have been 1/2. So I got myself a √3/2 when the angle is 60 degrees.
60 minus 15. We don't need that.
Correct, that's exactly what we're gonna do, but hold on, is there another time that sine would be a positive √3/2?
At-
It's at 120. Everybody agreed there at 120? It's right here. Same thing, same concept here. The y value is positive √3/2, and now we got an angle measurement of 120. So we have 2 times. And yes, you can do this in your head. Let me do it algebraically in front of us here. So all we do is we say a plus 50 is equal to 60, and a plus 50 is equal to 120. And then we solve each of those. So yes, A eventually is 10 degrees, and A eventually is 70 degrees. Oh, good. So we have a horizontal translation in our hands. Why we say that is we kind of just shifted our graph a little bit here. Okay.
But it's not even, it says so for all. So you do, but
Oh,
now it's
bummer.
60.
Okay, let's go with it here.
60 plus 360.
Go all the way up again, so, we're going to,
Are we good there? Hey, talk to me here. So because we add in the 50 each time, if we stick in a 10, we're gonna have 50, then we're gonna be at 60 before we take the sine value of it. And same thing here, if we're at 70, we add 50, makes it 120. Guys, this is so cool. We have learned how to solve trigonometric equations. Never did that before. We've got a robust system here. In fact, factoring, right? We can do quadratic formula. We can do a whole bunch of stuff here. So of course, you got to change this into radian measurement as well. So you guys, all yours. Can you solve this for radian measurement all by yourself? Of course, give you guys like,
Yeah, so it's gonna be
and it's a negative.
210 or 330.
Okay, you guide me. Tell me what to do.
You have to just get the reference angle of 30 degrees. For 5 and 3 and 4.
Uh-huh.
Sine is y, so it's be negative. So it's 180 plus 30 is 310. 360 minus 30.
Okay, let me write it out as you guys talk here. So this is 1/2, right? But we need to be in quadrant 3. And then also we need to be in quadrant 4 because we need to go under the x-axis.
we have to solve for radian solutions.
Or radian solutions, I gotta solve that.
We have to
Because we're just looking at unit circle, right?
Yeah. so
We're
what's
seeing our little
210?
formula sheet. Yeah. So looking at unit circle, looking for the radian measurement off unit circle.
6. It's 30 degrees, 5 to 6.
300 degrees.
7 pi over 6.
It's 200. Yes, 7.6. Because 180 degrees is pi, so that's pi to 6. There's 6 pi to 6.
6 pi.
And you
Okay.
add
Yeah.
1 pi to 6 to that.
So you're saying pi over 6 instead of 6 pi over 6.
No, I did it on accident, but it's not that.
That's 7 pi over 6, right?
Mhm.
Pi over 6 more than pi. Huh. Next one.
11 pi over 6?
11 pi over 6. Awesome. Got a little bit of work ahead of us though still. We've got some, oh man, some common denominators. That's no fun. So I need this right here. I need a 7 pi over 6, what, plus pi over 9, is that right? Common denominator of these guys, 18 probably.
18, 21 pi plus 2 pi.
Oh, running out of room here. 23 pi over 18. Are we good? Oof, okay.
Wait, is it the same thing? Oh, no.
11 pi over 6 plus
4
denominator is the same.
pi. Yeah. It
Whoa, no, I think this is already 33 pi here. Is that right?
was like 3, yeah.
Oh,
That was somewhere 7 pi over 6.
oh yeah, sure, no problem.
6 pi over 6 is 180 degrees equals pi, right? So that's 6 pi over 6 equals pi, right? And you know that 30 degrees is a rectangle and 30 degrees is pi over 6.
You think we add another pi over 6
Add in
to get to
right.
210.
Okay, and you put it over 6, you have the right one.
But you really are not even doing the calculation. You're just looking at your formula sheet. You're looking at the unit circle, right? And you're just getting that 7 pi over 6. Good there, no. Yeah, it's
We don't technically have to do that every time, we can just look at the unit circle, but it's not in front of me, so.
yeah.
The math part.
This is we usually do it just to do a circle,
Just if you're going to do off the unit circle, then you have to do it by calculator. And we did the calculator ones already.
Yeah, we'll always have the formula sheet there.
But just the calculator ones, if you're off the unit circle, you got to do it by calculator at that point. All right, you guys, finishing up over here. This is 2 pi, is that right? 2 pi. I got myself a 35 pi over 18. Is that the way it's supposed to be? 18 is made up of what? 6s, 2s, and 3s. 7 and 5.
That is not real.
That's not going to work.
Okay. You have to add the 2 pi.
Thank you so much.
We have to do 23 pi. Or no, it'd be.
It's 21 pi.
Sorry, yeah.
Is it 20? You guys, is it 23 pi over 18? Okay. Final answer for this one? 23 pi over 18. Is that right? Plus 2 pi k. 35 pi over 18 plus 2 pi k. Where k is an integer. Whoa, okay. You guys good there? Let me jump to. You guys talk to me. Should we do a homework problem or should I set up another problem for you? So,
It's gonna be one of the problems we have to do with the homework and all that.
yeah, so homework problem, or should I set up a problem? What do you guys say?
Homework, yeah.
Homework problem, okay. Let me get like a little tough one here, just so we.
We should set up a problem.
Oh yeah, this one, okay.
Oh, no, it's like.
45? Oh, God.
Think about it, it's really only like. Every other odd, because every odd that you have half is like 23, so every other odd is like 11.
That's still too many.
Just, it seems like so many. Oh.
What number is this?
Come on, man. Okay, I have probably 15, please.
Oh, yeah, got to do the root 2 here, non.
Oh, that's 2 over 2, so 45 degrees, and A equals 30 degrees.
There you go, Isabel. It's number 45.
Oh, it's 40 and the.
I'm pretty sure that's the test.
That's a book, yeah.
Okay, so, wait,
All right, let's talk about it together. Go ahead.
so we know that.
That's what I
pi over 12 is 15 degrees.
I
We
want to
know
look at
that 1 over root 2 is the same as root 2 of 2. which is
one second, Abel, one second. I just want to see. Okay, yeah. So your unit circle is actually 1 over root 2, right? It's not rationalized denominators.
Then it's
So,
negative.
but go ahead. Tell me. We're looking at unit circle.
So it's 180 plus 45 equals 225, and 360 minus 45 is 315.
I will give it to you here. So at 225, the angle measurement is 5 pi over 4, right? Because 45-degree angles always have a denominator of 4, as you sketch it out.
315 is just 7 pi.
Absolutely.
Okay. And then, yeah. We have to do. Minus what the heck?
Why do we have
equals that?
5 pi with 4?
That's kind of whack. 7 pi.
Go ahead, Isabel. Question?
How do we have 5 pi with 4? Because the negative 1 over 2 is a.
Because Abe said so. That's all. I'm gonna blame him for it.
225, right? 180 plus 45. That's in 5 degree, 4, 45 degree. Yes.
Okay. Yeah. Never mind. I helped him with it. That's all.
Wait, no. They look like they look similar. But they are. And you have to do. Then that's 5 pi. Isn't it supposed to be 7 pi over 6 on 7 pi over 6 on 7 pi over 4? That is 7 pi. Yeah.
7 pi over 4 here.
That's right.
Yeah, because it's in quadrant 4 right here. And so we just went in pi over 4, 2 pi over 4, 3 pi over 6. Oh, yeah, sure. 7 pi over 7 pi over 6. Where'd that come from? From the algebra right here. So we got common denominators. We had to multiply this by 3. This by 3 gives us 15. 15 minus 1 gives us 14. And then we got to reduce the fraction itself. So even though it was.
And 25 over 12 is 5 pi.
Just want to make sure, Dylan, does that make sense to you? We're just reducing fractions. That's how we got 7 pi over 6. We just did this right here, and then we just did that piece right there.
Oh, okay, yeah.
Yeah, 'cause these are- That's the A value or X, yeah. And then over here, we are subtracting, so 21 pi over minus pi makes a 20 pi. And Tristan, go ahead. Your question?
I was just gonna say that 5 pi. You were gonna say it first.
10 pi over 6 and 5 pi over 3. Yeah, cool. Awesome. Okay. Let me take a look at the back of the book. Let's see. Sure, right? We're almost done with that problem. Not quite done. I'll let you guys to finish because what are we missing here still?
Add a 2 pi then.
Yep, the 2 pi. X still needs to be added in. 45. 7 pi over 6 plus 2 pi k. 5 pi over 3 plus 2 pi k. Awesome. Okay, and one more that has a little trick to it. So we might as well see it right now. This is exercise 14, but for us, it is problem number 29. Every other odd, every 4, 28 plus 1 is 29. Okay. This one's the one that was kind of tricky during the lecture. So let's do this one together here. Let's see if this helps. Oh, actually, no, you do that to tangent and it's fine. Okay, it's set equal to 0. That's the trick. Otherwise, we would not be able to do this. Theta.
So we know that.
Oh, if we move it over, then it's going to get more complicated. The little trick here is the fact that it's set equal to 0.
Wait, is it sine of tangent theta?
Oh,
We
sorry,
got it.
sine theta, tangent theta.
Root 3 tangent theta equals 0.
So it's just 25.
Not tangent.
It would be 90. Right? And it's just 1 over x. So just 1 over 0, 0 over 1.
Say again, Dylan, say again.
If you're trying to find where tangent equals 0, it would be 0 over 90 degrees, right?
True. Yeah. So that's the kind of, so you're guessing and checking, right? But where's the algebra piece to it is the fact that if I have 2 terms with tangent inside them, this is what Dylan's doing in his head. He's saying, when is this happening?
So just put it equals 0 anyways.
Yeah, and the step before that is we're just going to factor. Right? When you have this right here, it's a factor step, and the reason why we can factor is because it's set equal to 0.
Wait a second, so factoring, in that method, that kind of, way that we do products, that can also find just any function.
Absolutely.
Now I know that tangent theta equals 0 and then root 3 minus 2.
Yeah, that's exactly what Dylan was trying to figure out right here, right? When is tangent theta equal to 0? Because if I have 0 here and 0 here, who cares about anything else? It's going to give me a 0. And that happens when?
0, 1.
Say again?
The tangent theta is 0 at 0 or 90 degrees, right?
Oh, wait, yeah.
It's 0, 90, 180, or 270.
More because
Well, if there's just a 0 in either one of them, it's 0.
that's true.
Oh, wait, no, if it's 0,
It's undefined, yeah. So it's only at 0
So unit circle says this here. It's
so it's
the
at 97. Wow.
It's y
Oh,
over
yeah,
x.
you're right. It's 90. No. Yes.
You want 1 over 0.
It's 0 and 180, I think, because x has to be, you have to have 0 over 1. Then you have 1 over 0, you're screwed. So it's 0 and 180.
No, it's 9270 because the y component is. Yeah, you're right. Never mind.
0 degrees and is it in degree terms? Let's see. Yeah, degree terms. And 180. Everybody agreed there
Yes.
for that one. And then if we solve this here, subtract square root of 3, divide by -2, you have ourselves this concept right here.
Looks like 8.
let's see, I move the negative, I move it over once, I divide by negative, should be a positive, right?
Oh, yeah.
So that is.
I'm gonna see quadrants 1 and 2.
Yeah, it has to be, but it's degree numbers. Wow, okay, 30 or 60, and I always screwed that up.
I don't know.
30 degrees. No.
Because
60 could be bigger than 1/2, yeah.
sine controls the y,
So that's at 60. and
sine
one-
controls the height, and you want the bigger height for root 3. Therefore, it is that right
Should I just write all those out?
Yes, but at least we did that piece. And yeah, that was the one that was kind of, we got stuck on in lecture. So I want to make sure that we saw that at least. All right, the rest of it, you guys have a good weekend. See you guys on Monday.
We can do all the.
We can do all the